Hello everybody and welcome to our presentation. My name is Sam and I'm gonna to illustrate our project pathway. Absolutely, I will do it with a combination of my group mates. The title of presentation is Design and Analysis of a Floating Solar Powered Reverse Osmosis Drinking Water System for a Restaurant in Kish Island in Iran. Now let's a brief look at the list of subjects. After introduction and literature review, this presentation will cover site specification and water configuration, water system consumption and load sizing for the site, PV system design, optimization and analysis, dynamic simulation and control system design. World is forcing by a growing demand for drinking water. Traditional reverse osmosis desalination are common but require a lot of energy. The nexus between energy and reverse osmosis technology represents a critical aspect of water treatment systems. Integrating solar power into reverse osmosis system holds promise for addressing fresh water scarcity and concerns about climate change and sustainable development. For more efficiency, we need excellent solar radiation and a structure for floating. Floating photovoltaic systems are a new option for installation on water compared to previous land and rooftop installation. They are positioned on floating platforms made of plastic or stainless steel instead of fixed rack. The approaches of this project are Hummer and MATLAB software. For more study, I delved into many reliable articles related to the project title, and I brought some of them here. For example, Sheikh Osman conducted a comprehensive study on a photovoltaic reverse osmosis system optimization for a town, and Mohammed Musavi studied Homer Pro for photovoltaic reverse osmosis system optimizing for a rural house in Tehran, Iran. Now let's turn into Mohammed for continuing.
Hello everyone, thank you for watching our video. My name is Mohammad Kashif and I am another member of this project, and let me explain you about the site specification and what are the challenges and what are the water requirements in that area, the site we have selected. So in 1979 the water sources that were available in Iran were 3935 meter cube per person, but now they have reduced and dropped almost to 50%, and now only 7732 meter cube water sources is remaining, and that indicates that water scarcity is also a very great issue in Iran. And uh, the but the good thing is the irradiance and solar resource which is available in Iran is very good, and it is almost 5 to 7 kilowatt hour meter square per day, and the sunshine hours per year are also high, from around 1500 to 3000 per year. So water source is available, and PVRO system is a very good idea. So through PV based RO system, installing RO system, the seawater can be made available for the population as drinking water. Thank you. Hello everyone. Thank you for watching our video. My name is Mohammad Kashif and I am another member of this project, and I will explain about in this slide about the site specifications and water configuration. So as you can see that in 1979 the water sources available to Iran were 3935 meter cube per person, but now only 50% is remaining, that is 1732 meter cube. So that indicates that fresh there is a huge challenge in Iran for the supply of fresh water, And what are the main basic reasons? These are due to the environmental factors such as the closed rivers, diminishing lake volumes, and escalating droughts that are contributing to water scarcity. But the good news that good news is that Iran has abundant solar resource available, and that is 5 to 7 kilowatt hour meter square per day, and it has also good amount of sunshine days throughout the year. So there is an opportunity that to face the challenge of water scarcity, we can install PV based RO systems that can solve both the problems, that can provide fresh water to the community in Iran, and also not harming our environment and powering it through sustainable uh, PV system. So for our study, we have selected a restaurant in at Kish Island, Iran. The location of the restaurant is mapped, presented in the pin location on Google Maps, and it is a waterfront restaurant for that is very popular for tourism industry. People come here and enjoy a scenic view in this restaurant. So the all the general loads of the restaurant are supplied by the grid, but this essential RO system will be supplied by an independent supply would be of PV. So this is the sustainable solution to provide uh, fresh water source to the restaurant. And as we if the water quality, the TDS value, total dissolved solids value, was found to be 39200 milligram per liter in the sea water which is available in the sea. So there is a need to for good and advanced water filtration so that this water can be consumed. So, what is RO system? RO system is basically reverse osmosis that treats unfiltered and untreated water and converts it into a clean water by passing it through a pressurizing pump through a specialized membrane. And this membrane, each membrane has have small holes through which water can pass, but the contaminants are blocked. So, in this way, uh, this system works, and clean water is converted, untreated water is converted into clean water. So as far the sizing is concerned, in this restaurant per seat water requirement is 70 gallons per seat, and through this we can estimate that the amount of energy which will be required to run the PVR system is 10.7 kilowatt hours per day. And also a brackish tank is used which has a capacity of 4000 liters, so that when the motor is running, so fresh water can be stored into this system. So, as per the calculation that we made in the way concluded about the water requirements in the previous slide, so these are the load which we have determined: a submersible pump of 1.2 kilowatt and RO system feed pump 0.6 kilowatt. 200 watts are dedicated for miscellaneous load, and so total load requirement becomes 2 kilowatt. So the major components of our system are these: panels, batteries, and inverters. So Canadian Solar Max Power CS6U 340 watt panels are selected, and batteries, lead acid batteries of Trojan SAGM 12205219 ampere hours are used, and 4000 kilowatt Struder extender inverter is used, which has a 48 volt bus. So our batteries, which I have 12 volts, will be four batteries will be connected in series to make one string, and the whole system will be optimized by Homer Pro software, so that we can get how much panels and how much batteries and how much inverter capacity is required. So these are the three main components of our system.
Hello everyone, happy to have you here. In this slide, I'm going to explain you about our system design using Homer Pro software. As you know, Homer Pro optimizes hybrid power systems. It helps us integrate different components to get a cost-effective solution, and we can maximize the usage of renewable energy. As explained in previous slides, our system is an AC load which is connected to AC bus. Energy consumption based on calculations done before is 12 kilowatt hours per day. The peak is 2.61. The power generation is done through a PV system, and the amount of generated power is 4.16 kilowatt by connecting 12 panels, each with 340 watt power. And the Homer Pro recommended us to use 12 volt batteries in 4 battery strings to get a 48 volt DC bus voltage effectively. And then the DC bus voltage is connected to AC with an inverter to convert DC voltage into AC. The capacity of this inverter is 4 kilowatt, and as you can see, it is compatible to use in 48 volt DC. Now let's delve into the cost analysis performed using Homer Pro. As you can see here, net present cost during the project's lifetime, which is considered to be 25 years, is about $19,000, and the cost of energy per kilowatt which is produced by this system is only 0.33. It seems to be reasonable and competitive price. Also, you can see the cost analysis for each component of this system here, and according to this chart, the battery system seems to be the most expensive, and on the other hand, the PV panels proved to be the most cost-effective component of this system. In this slide, you can see electrical analysis of Homer Pro. After Homer optimization, the excess energy which is produced by the system is only 29%, which seems to be a good percentage. And also the total system, including PV and battery, will produce 6,671 kilowatt hour per year. And here you can see the monthly electrical production here during the year. As you can see, May is the highest and December is the lowest. It is clear it is just because of the different irradiations of sun. Now we're going to do the dynamic modeling of the system. Before that, I just want to show you the block diagram of the system to be able to explain it in a more practical way. As you can see, the PV array is connected to DC bus converter. This is the main purpose of this block is to decrease the output voltage of our PV to be suitable for our battery system. The DC bus voltage, as mentioned in previous slides, is 48 volt, so we have to step down the voltage of PV system. This task is done by the buck converter. Then we have to convert our DC voltage into AC since our load is AC one, as explained before. And you can see the inverter is just converting DC to AC, so the voltage should be increased to be suitable for the load, which needs RMS voltage value of 220 in 50 Hertz. So here we use a step-up transformer for increasing the voltage level. In a total system, we are using two controller. You can see them in yellow. We have MPPT controller and inverter controller, and I will explain each of them in its own part. Okay, now we need to explain the block diagram in more detail. So the PV system consists of 6 parallel multiplied by 2 series panels, and the output power is about 4000 kilowatt, and the output voltage at MPP point is about 75 volt. This amount should be decreased to be able to use by the battery system. So the DC bus voltage is 48, so buck converter is used to step down this amount of voltage to 48 volt. Battery system is, as you know, a bidirectional element. The system will be charged and discharged. So based on recommendation by Homer, 12 batteries, 12 volt, 3 string of 4 series lead acid batteries are used. They are connected to 48 volt DC bus. An inverter which convert a DC voltage of DC bus to AC to be suitable for our load is used. It is a single phase full bridge 4 pulse topology, and it works in 50 Hertz. Then we have to increase the voltage to meet our requirement at load side. So a step-up transformer is used. The output voltage will be about 220 volts RMS, and as I told you before, the load is AC, and it is a single phase asynchronous machine. The power as it has been calculated in previous slides is 2 kilowatt, and the frequency 50 Hertz, and the RPM is 1500. Here is an explanation of the incremental conductance method, which we used for maximum power point tracking in our photovoltaic system. It is clear the objective is to continuously track and operate the PV system at its maximum power point, which is here. The method utilizes the ratio of change in current to change in voltage as a reference. By comparing this ratio with predefined value, which is this much, the direction to adjust the operating point is determined. The system just compare and conclude if we are in left hand side or right hand side. If we are in this region, the duty ratio should decrease, and if we are in this side, right hand side, the duty ratio should increase. Okay, now we are going to talk about the inverter controller. As you can see and explained before, the load side is an AC load which requires 220 volt RMS voltage. So the purpose of this controller is to get fixed output voltage at load sides. So we use proportional resonant controller, PR controller, to get zero steady state error. As you can see, the voltage and current from load sides are used. They compared with a reference value, and then using some integration, some gain adjustment, and other control techniques, a reference voltage is generated. Comparing with some signals, the PWM generator will use this reference as a signal to feed into inverter as a gate signal, controlling the on and off state and regulating the voltage on the load side. Here you can see the PV battery MATLAB simulation. Let me show you different part. This is the PV system, MPPT controller, buck converter, battery system, inverter, and a step-up transformer, our load, which is a synchronous machine, PWM generator, and here is the inverter controller. As explained in previous slide, here you can see the functionality of inverter controller. In our load side, we can see a pure sine wave with RMS value of 220 volts, which is required by our load. As stated previously, the load is a single-phase asynchronous induction machine as an RO system, since the load is compressor mostly. You can see here that the rotor speed is fixed and in our desired value, which is 1500, and based on our calculation, the torque is also in desired level. This is the same about the current of our load, which is shown in this graph. In this page, you can see all references used in our project. Finally, our presentation is over. On behalf of our group, I extend our heartfelt gratitude to our dear professor and TAs for their invaluable contribution throughout this project. Thank you.